Here we go. I did PLTW Truss calculations, so POE statics video. I did PLTW Truss calculations.
PLTW.
And then
you say it's the
POE statics video, I think this was.
So this is negative. That's why this is.
It's by Chad Brooks. Yeah. Okay.
what's his name?
Chad Brooks 22.
All right, folks. I think we lost two of our friends.
It was POE statics video number 5.
So, again, with my students, I make these a little bit bigger on the screen, but I've already presented them. The students already have these in their notebooks. This is one of the rare occasions on which I hammer to my students, you know what, it's okay to skip a page or two because we're going to fill those up. Yes, I know that that's, scary, but we have to accept that that's just what's going to happen here. So we would do, Truss B on a page, leave a page or two open, C on a page, leave a page or two open, D, etc.
Yeah.
Okay, so now we get to the really fun part, the method of joints. There are multiple methods for solving trusses. This is by far the easiest, and it works for simple, statically determinate trusses. There are complex trusses, like G, that one that had that weird piece on top where it was the two Warren trusses with a weird piece to hold them together. Truss G is not a simple truss. You cannot solve the whole thing using just the method of joints. You just can't. So, recollection. We've got our vector with magnitude f at angle t, sigma y equals 0, sigma x equals 0, sigma m equals 0, sine, cosine, tangent. I made this really big image here because I can pull that out and I can actually print that on sheets of paper and tape them around the room. Hint, hint.
Yeah.
So when I provide this PowerPoint to you, that's a thing that can certainly happen if you choose to. So let's go for our little truss, our darling little truss. Truss B, if you will. We've already verified static determinacy. We've already calculated our reaction forces. We already know that angle A is 60. It says assume, but that's just a pedantic mathematics phrase. So what we want to know is what's going on now inside the truss. And the kids are like, well, why does that matter? It matters because we want to know what materials can we use to make this truss. And then the kids are like, well, why does that matter? And we actually have some time in our courses about this. We spent a lot of time, we have a whole unit on it in aerospace. We spent a lot of time on it in CEA. We spent time on it here in POE. We spent time on it in IED. In other words, in almost every single one of our courses, we talk about the material choices that we use. We talk about recyclability. We talk about structural stress. We talk about availability. We talk about the fact, or just the expense of the resources. When we were looking at the JSF project, there's a really nice documentary about Boeing and Lockheed competing for the JSF contract that eventually turned, Joint Strike Fighter, that eventually turned into the F-35 Lightning II debacle. And Boeing's offering was this really neat looking plane that had a single piece of composite fabric across the entire top of the plane, and behind the pilot was a milled single piece of titanium that was like this big, this huge slab of titanium that then got milled out. They would have to mill it out for each individual plane. And they wound up being behind schedule because they had to invent new methods for doing the composite fabric for the top of the plane so that it would be completely smooth and not have any bubbles. Really cool stuff. Great documentary. if you need an emergency sub plan and you want your sub to be able to just put in a movie and hit go, great documentary.
What's it called?
What?
I don't remember.
I think I've seen that.
But yeah, it's
Oh,
about
the award
It's about the Joint Strike Fighter, Boeing versus Lockheed. It really, really cool, and I can't for the life. I think it's an episode of Nova, whatever it is. It's out there and it's great. And so we need to know what's going on inside of the truss, because it's ludicrous for us to use, titanium if steel or aluminum is going to do the job. It just doesn't make any sense. The best engineer is not the engineer who builds the strongest bridge.
Battle of the X-Planes.
Thank you. Battle of the X-Planes. The best engineer is the one who builds the weakest bridge that does the job. The least expensive bridge that does the job. And especially, we all know this, we're all, and we get this complaint from our parents where we're like, oh, low bid, blah, blah, blah. It's literally a law. I don't know about where you teach. It's literally a law in Maryland and in Baltimore County that if we triple bid, as long as it meets the specs, we don't get an option anymore. You have to take the lowest bid that meets the specs. So go ahead and complain all you want, vote. So that was a conversation that we had with my kids recently about one of the projects, the bridge project, because some of the kids were building these really expensive bridges in West Point Bridge Designer. I'm like, you missed the point. So we're going to stay organized. We're going to create a table. And our table is going to have some really important pieces of information. Up at the very top, we're going to get super cool and fun. And where we're going to start with our table is this pair of columns over here on the left. We're going to identify our loads, reactions, and members. Start with your loads. Your external load on truss B is at joint B. Your reactions are at A and C. And then all of your members. I do my members alphabetically. So AB, AD, BC, BD, CD. By doing them alphabetically, it keeps things organized and it helps ensure that you actually get all of them. If you wind up in a situation, especially in some of our more complicated trusses that may have 17, 18, 19 members, if you miss one, this gets wonky. Notice, in our master table, that's what we're calling this is our master table. In our master table, we don't care about f sub x and f sub y. We don't care. We cross those out, we black them out, whatever you need to do. Don't care, don't care, don't care. In our top of our master table, in our f sub y, f sub x, we have our components and our composites. Because it is possible that some of our forces may be applied at an angle, and as a result, we may need to break those down into our composites. Excuse me, our components. But positive and negative, quite frankly, don't matter. We're going to get a fun definition of positive and negative when we get down to top. Down here, we have just our composite force, just the magnitude of our composite force, and we're going to highlight whether it's positive or negative. And again, we're going to have a special definition of why that is. So, what I do at this point is I make sure that my students have they build this table. So I'd like you to go ahead and build this same table instead of obviously markering out f, y, f, x, and plus, minus, and do a big slash through that. This is one of the great things about the students using grid line paper. This year we went to one-to-one devices, little Windows laptops. And so we're using OneNote as their notebooks. And the cool thing about using class notebooks in OneNote is if I do a notebook check, I can, since I created the class notebook, I can go in and I can just check them on my own whenever I feel like it. So I can do a notebook check and they, panic, scramble to get their notes in. But they can apply a grid to the background of the page, so they can draw these on their own, or they can go in and they can insert a table, or they can go into Excel and they can do this in Excel and then insert that or do a copy and paste, whatever the case is. There's a lot of flexibility in terms of doing this. Excel is a wonderful, wonderful tool. We stress it a lot in aerospace. So if you've got the AE program at your school, your AE teacher, which might be anybody in here teach AE? But we are really pushing Excel as a tool over the last couple of years. Getting AE. Welcome back.
Sorry.
Nah, it's all right. It's all right. Yeah, you'll be able to catch up. So basically, what we've done is we're creating a master table for Truss B.
Oh.
And so you'll be able to catch up. So I think we're about ready to click on the next page. So what I do with my students is I have them create their master tables for all of the next upcoming trusses, or what I'll do is I'll assign this as effectively homework. So if this point comes in the middle of a class period, I'm not necessarily going to take the rest of the class period to say, oh, okay, burn that, make your master tables. I'll say, make them tonight. When we get back next class period, then we'll start that at the beginning of the class period. Most of your students are going to do okay creating these. If you get a student or two who runs into trouble, tell them to email you. Each table gets its own page, which again goes against our rules of notebook keeping, but for what we're doing here, it's going to be fine. And then, yeah, so this is where we go. Okay. Now we go in and we look at each individual joint, hence the term method of joints. When we look at each individual joint, we assume that that individual joint is the cheese that stands alone. We create a joint table and we sketch the joint. Now, in the curriculum, they have you kind of doing the same thing with a pseudo free body diagram, which is kind of what we've got going on here. The diagrams in the curriculum and the way that we've got the Word documents set up in the curriculum, I just hate them. I don't find them. I don't find them to be very effective at walking the kids step by step the right way without first walking them through myself step by step. So that's what this presentation does, is it walks them through a separate example, giving them much more confidence, I have found, in walking through the actual activity 2.1.6. Yes, 2.1.6. So, we fill in what we know. In terms of our joint, A, we literally take that line from our, sorry, I skipped back, but we'll come back. I just took it from our master table here. We've got 25y, 0x, 25f. Y, 0f. And our members, A, B, and I assign a theta. I give it the angle. I identify the angle. AB, relative to joint A. That's the key, relative to the joint. AB is at 0 degrees because it is pointing directly to the right. So it is at the positive x-axis, it is 0 degrees. Because it is at 0 degrees, none of the force in AB can possibly generate any force in Y. Sine of 0 is 0. Thus, f sub y cannot possibly exist. It's just gone. So cross it out. Don't even put a 0 there. Even though mathematically speaking it's a 0. Don't even do that. Just cross it out. Because I want the kids to focus on the fact that that's not a thing that even exists. It's just gone. AD, on the other hand, at 60 degrees, because it's at 60 degrees, we know that it should have something in X and something in Y. So we leave both of those open. And of course, we don't know the full force in AB, and we don't know the force in AD. So that's how we've set up our joint table. So we've got a sketch of our joint, we've got our joint table, we are ready to rock this thing out. Are we ready to rock this thing out? All right. So, here's where, and I sort of accidentally gave away the answer. Here's where we go and we ask the kids, okay, we have 3 equations. Well, we had 3 equations on the outside. Moment, y, and x. Moment, x, and y, whatever. Moment, is moment a thing here? I'm implying an answer by the way I'm asking. Why not? Why isn't moment a thing here?
We're not looking at rotation.
Well, I mean, we are, but we know that that's not going to be something that can happen. Why aren't we looking at rotation? Okay, but even if we were at joint B or C or X, we'd have the same situation. Why can't we have any rotation? And it's not because it's a pin. Because notice that I don't even show that it's a pin. It doesn't matter that it's a pin. What matters is that we are just looking at the joint, so there's no distance. There's no distance. So this force directly toward or away from the joint, this force directly away from the joint, this force directly toward or away from the joint, there's no distance. Therefore, there cannot be any moment. So, sigma m, gone. The benefit is, cool, that's one equation that we don't have to worry about. The downside is, that's one equation out of our toolbox. Because remember, we used that as a tool earlier to help us solve for y, but we don't have that in our toolbox anymore. So we have to look in our table here. This column is not going to help you. This is your output. This is not an input right now. These 2 columns are where we are focused. And the cool thing is, we know that our equations represent these 2 columns. F sub y, f sub x. The sum of f sub y has to equal 0. The sum of f sub x has to equal 0. In other words, we have the sum of y, sigma y, is a sub y plus ab sub y plus ad sub y, but this doesn't exist, so it's this plus this. All right, so that's one unknown. Sigma x, a sub x plus ab sub x plus ad sub x, that's 2 unknowns. So, which of these 2 equations can we tackle first?
F sub y.
F sub y, or sigma y rather. Because that's the only one that has 1 unknown. We have to go for the one with 1 unknown, so the joint itself, based on what we know, tells us that our only option is to go for y first. There are going to be some joints where you may go for x first. This one happens to be the case that y is the only path. Cool? Yeah. So, sigma y, a sub y plus ab sub y plus ad sub y has to equal 0. Yes, when I'm starting out with this, and sometimes all the way through it, I require my students to write that equation right up top for every single joint. I want you to show me what you're including in this equation. Because if you screw up that, you're never getting the right spot. And that's fine. I'm gonna find you. I want your breadcrumbs. At the very least, we'll make a nice little crust for our mac and cheese. So 25 sine of 90 plus AB sine of 0 plus AD sine of 60. Yeah, I skipped ahead a little bit, because remember, all that stuff that we did a couple days ago, where we figured out how to do our component vectors, A sub y is 25 sine of 90. That goes back to what we did just a couple days ago. Remember, that was a couple days ago. For us, it was back now. We wind up with 25 plus AD sine of 60. AD equals negative 25 divided by sine of 60. And notice, this is AD. This is not AD sub y. This is not AD sub x. This is AD. Your kids will get goofed because they're thinking that they're solving for AD sub y. No, you here are solving for AD sub, AD sub, AD, just AD. So AD equals negative 28.87. That is the magnitude of the full force in AD. But the benefit of that is that from that number, we can calculate AD sub y and AD sub x. Once we get AD, we can apply our basic trig to calculate the component of x, component of AD in x, and the component of AD in y. So negative 28.87 times sine of 60, negative 28.87 times cosine of 60. Super duper simple. We love it. It makes us happy. It's boom boom. Takes a couple seconds. And we take that information and we will put it in our joint table, which I'll wait just a moment because I see pens flying furiously. This is one of the, that's really annoying, whoever's getting texts out there in the vestibule. Okay. Is that when you're putting on library? This is one of the rare occasions where I do allow my students to use pencil for mathematics. That's right, I make them use pen. For doing the calculations, I want them to use pen, but for doing the table, I let them use pencils. Let's launch it. Cool? What do we get? Or are we still getting? We're still getting. That's cool. That's totally fine.
I put it there just for you. Put that there just for you. I put that there just for you.
Oh, thanks.
No, I just got it up my way.
constructing